Hi, in this video I'm going to give a review of this paper called CORTEX, a compiler for recursive deep learning models. I understand that this is like a domain-specific language in the lines of Halide, Tiramisu, Taco, and TVM, and more in the lines of TVM because this is developed for Python and it can be seen as an extension for TVM. And it was developed by OctoML, which is a TVM-based company, and Carnegie Mellon University. So unlike TVM is for deep learning, Halide is for image processing, and this is for recurrent layers like LSTMs, GRUs, RNNs, and you're going to see those in the benchmarks that they use for getting their numbers. So one curiosity that I found in this is that they try to outperform the state-of-the-art that they try to outperform is DINET and CAFS. And both of them were developed in 2017. And they were also developed, at least in part, by Carnegie Mellon University, similar to this paper. So it's kind of curious that after 6 years, a new state-of-the-art DSL is developed for these recurrent layers. So in 2017 also was the date of the Attention is All You Need paper about transformers, and I understand that many people, including myself, thought that transformers are going to get rid of LSTMs, recurrent layers, and stuff like that. So it's interesting that the same university, after 6 years, developed this technology for recurrent layers. So the recurrent layers, according to Carnegie Mellon, are not dead. They are still very much alive. Okay. So the approach that they use is similar to TVM and Halide. They basically separate computation from schedule, and they provide high-level primitives for optimizations. They provide these compilers that are portable. And potentially, I understand that you could put an auto-scheduler on them, and the performance that they got is, I think, up to 14x over the libraries, the different alternatives. Okay, so this is the example, the main example that they provide. So as you may know, recursive layers like LSTMs are good for natural language processing and other similar applications. I understand that they can be used as well for source code and even perhaps DNA as well. So they rely in here on these structures. In this case, it's going to be a binary tree. So they basically parse the "it is a dog" phrase, and they create around this binary tree, and that is fed into a recursive algorithm that is going to process it. So you can see that if it is a leaf, you are going to get the embedding of the particular word at the place where you are, and then you go to the left, go to the right, and then you get the corresponding embedding. And then you just add the embedding, apply a tanh function, and basically until you got the whole embedding. So this is basically to get the embedding for this whole statement. Okay. They begin with the argument that all DSLs have, that of course you can do manually optimized libraries for these recurrent neural networks for particular targets. That's very costly, and basically that works for if you have a limited set of targets, but as you may know, there's a bunch of targets out there and they're always changing. So it has been found more practical that you have these DSLs that are able to take as an input the input program, the sizes of the program, and also the hardware target information, and basically come up with an optimized algorithm. So those are that's what the DSLs do. Halide does it, TVM does it to some extent, I understand, and also that's the idea behind here, to make a DSL that is portable instead of relying on fixed libraries. So this one in particular is for LSTM. I mean recurring layers. And this is a very important point that they bring in here. So when you're dealing with optimizations, these libraries deal with one optimization at a time. For example, I'm optimizing this LSTM are optimizing this matrix multiplication. But in deep learning, we know that there's an architecture, and there has to be optimizations between these layers. So that's something that this Cortex paper, as well as highlighted, because it's not only fusion that is enabling these DSLs, but also partial fusion, like the computat primitive. So, and not only those optimizations, but other optimizations as well. So when you combine that with the other scaling primitives, you can come up with some optimization of the whole system rather than just one isolated node. And these DSLs, like TVM, Halide, that and now this one and others, have these high-level primitives that allows you to explore these state spaces easier than manually implementing the optimizations by yourself in these huge nested for loops. Then if you mix them with a whole architecture of a deep neural network, is impossible for manually optimize, and you can have so many architectures that is impractical for a human being to come up with all the optimizations, all the global optimizations for these mega networks. A model persistence and optimization that they mentioned, that I understand it to be like a parameter reusing, that is difficult to do with vendor libraries. But when you have a representation of the whole network or a subset of the network, you can do those source optimizations. Yeah, so he mentions another nimble from 2020 that relies on auto-tuning for individual kernels. So basically the author is stressing the importance of global optimizations that these type of DSLs are able to cover easily. And of course, Cortex is going to provide this kernel fusion and model persistence. I understand that is also partial fusion, computat, rather than full fusion as well. Full fusion is possible, of course, but partial fusion should be possible with what they have. So recursive models have the following 3 challenges stated there. Okay, so these are more like the requirements that they have. One of the key features is that they want to model the recursion in a convenient way in the intermediate representation. They want to represent the recursiveness in a way that they are able to optimize it without hindering kernel fusion, and allowing things like dynamic batching, making it easier, and they want to perform this optimization statically. So they want to allow the unrolling of recursion as well. Yeah, basically states again that the Cortex is a compiler framework for enabling to be able to express iterative and recursive models to generate efficient code across different hardware backends, CPUs, GPUs. That's the goal of the DSLs. Support many backends, and also they have the insight that a control flow in recursive model often depends solely on the input data structure. This is key. As I mentioned before, how they handle input data structure, they understand that they linearize it. They do some serialization of it before processing it. So they work at a high level and then lower to to for loops eventually, like any other DSLs that works at a high level, and then you get the for loops later. And they will have these scheduling primitives for doing the specialization, dynamic batching, and also the computation hoisting, which I understand that this is might be related to the persistent thing that they mentioned to extract, reuse constant parameters. So I guess they have other scheduling primitives for optimizations as well. I found this interesting. Okay, so Cortex it basically takes a compiler-based approach. It doesn't follow the black box optimization of vendor libraries, and it enables extensive kernel fusion. That's a big one for them, and avoid many of the overheads that other state-of-the-art options like Dynet and CAFs do. And it's gonna has a table for that in here. But this is what I found interesting. Basically, they extend the tensor compiler from Bragg and Kelly, the author of Halide and Baghdadi. And by extending it, it allows them to use the opens the door to use the autoscaling, like Mujapudi and Adams, which are the autoscalers for Halide. I just noticed what CORTEX means. CORTEX comes from the abbreviation of Compiler for Recursive Tensor Execution in here. Okay, so here's the comparison against the state-of-the-art alternatives, CAVS, DINET, and Nimble, and PyTorch. So here are the optimizations that the paper is focusing on dynamic batching, model persistence, and kernel fusion. So none of them have kernel fusion. This is bad. So I understand that this might be the first DSLs for recursion. And then notice that the yes is bad in here, so that's why it's red. So only Nimble is library. I mean, it's not library based. So this is library free. So this is portable. This is a huge. Even that's the thing. This is gonna outperform the status quo, but it's also portable. So that's a big advantage because you should be able to have this working for many targets rather than a fixed target when you have a library. So yeah, it has dynamic batching and model persistence. Okay, so here again is a summary of the contributions of this paper. They provide a compiler framework for end-to-end optimization for a low latency on inference. So this is a key here. They are focusing on inference, not on training, for recursive deep learning models. And they provide some abstractions for this optimization, and this is key. It's good to have. It enables autoscalers to do this automatically. And they evaluate it against the state-of-the-art recursive deep learning frameworks. Okay, so let's go to the overview. The author mentions that recursive deep learning models generally traverse recursive data structures while performing tensor computations. Actually in this paper is the first time I see that you traverse a recursive data structure for a recurrent layer. I understood that these recurrent layers basically have a state, and you basically feed an input vector of data that you don't know the size of it. So I understand that this data structure facilitate to do this through recursion rather than through iteration. So of course the dynamic control, the dynamic nature of the problem makes it difficult for optimizations such as kernel fusion. And yeah, basically they want to convert this into a loop eventually, which that's what it is dynamic, so you're gonna get a loop for it, but they want to do it efficiently. Okay, so here are some observations that are key for their design. First, that the control flow depends on the connectivity on the data structure, not on dynamically computed data. And the graph, I understand, can be traversed beforehand, so you can do some pre-processing to it before going into the tensor computations. And also there are recursive calls that are independent of each other, which enables parallelism. Property 1 means is the assumption that the model is capturing a data structure instead of just data floating. An infinite or indeterminate sequence stream of data. And also property number 2 means that the computation can start at the leaves and then move upwards. And basically property is allowing parallelization. Okay. Yeah, so this is an overview of the CORTEX compilation and runtime pipeline. So the entry point for this diagram is going to be what they call the recursive API, which is in number 1. You can see it over here. We saw in the first figure in which we declare a recursive relationship between the computations to determine how we're going to process and input recursive data structures. So this is your input, which is which can be a sequence of tokens that are accompanied by this, in this case, a binary tree, or it could be, I guess it could be another structure, another graph, another DAG. So if you're familiar with Halide or TVM, this will be the computation part. Yeah, of course, it says it in here. And this will be the scheduling part. So these are the scheduling primitives. It's basically what I alluded before about separation between computation and scheduling. That's key, basically, because you have a single computation and then the optimization are expressed like this, and you can have an auto-scheduler that finds the best combinations for the particular input problem. So in this one, a dynamic batch is applying to the whole algorithm, but this one in particular seems to be applying to this particular node, the specialize. Once you got the input data, the input program, and the scaling primitives, eventually you want to get to a generate optimized code. But before that, you have to go through the intermediate representation and the lowering. Okay, so the data structure is going to be linearized. Section 4.2 talks more about it, into these batches. And the way that they organize it is in such a way that the data dependencies are met, so that it's easier to parallelize it. So basically at this point, the program doesn't care about control flow because that's already expressed in the way that is linearized. So it's linearized in a way that is convenient for parallelization, and that you can do optimizations more freely in your code. So notice that we're gonna have these structures for the left, these arrays for the left and right nodes. So these are gonna be the left nodes. This is 1, 2, 4, and 6. Those are your left nodes, and the right nodes 8, 7, 3, and 5. So as you can see here, this is the high level recursive API is gonna be lowered into the intermediate iterative representation, which is the irregular loop IR. And notice that you access by the index of the words, but also you have the other index because the embedding is gonna have a 256 elements on it. So that's the array that you're processing for the embedding. And then you get the left one, the right one, apply the tangent, and basically compute for that part, the embedding for that particular node. So basically you traverse it all the way until you have the node number 0. And yeah, so basically you lower it even more to get the generic code and run it on these linearized structures. Okay, so this is a simplified implementation of the model in figure 1, the first one that we saw, which is this one. So this is the actual API for the array. I always forget the recursive API, for the recursive API. So in the tradition of Halide and TVM, this API looks easy to read and elegant, and also like Tiramisu and TVM, they have a compute keyword for the computation. Halide doesn't have that, and they're gonna express the computation with the compute. For computations is this one. You're gonna get this a computation, 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 and computation. Okay, so the inputs are gonna be the embedding, and then this is the dimensionality. So you have the vocabulary size. So you have to put a word in here, and also this is the hidden, the embedding size, the size of the embedding, which is going to be 256 for this example. And the input tensor is the number of words. In this case, it's going to be this number of nodes. I think it's 8 or 9. Okay, so then this is a key concept in the recursion. They have these placeholders, which is a first-class citizen for recursion. So that's how you handle through this. You handle recursion. And okay, so the computation is going to be a lambda that takes the input indexes, and then you just go access this embedding, get the word from the particular node, get the word, and then with the index you get the output. That's for the leaf. So this will be this one. And then for the left hand side you have another computation, and for the right hand side another computation. And notice there's no placeholder in here because this is a leaf, but the recursion is going to have a placeholder in here. And then you have the node in the left, you get the index and the right index. You see that dimensionality is the node and the particular index, so they match in here. So that's your left computation. And then the recursive case, yeah, basically you basically have another computation for mixing them both together with a tangent. So yeah, you have a tensor. The output of the computation is going to be a tensor similar to a func in Halide, and then you just access them to get the output, the recursive case. This is the output case. So for applying the recursion, they have this special, I will think that this is a special computation, the if then else, in which you have a conditional on the index, and then that conditional is going to determine which computation are you going to use. And it could be the left case, the leaf, or the recursive case. So this is a computation. So this is just a computation. So you put a computation here. So I understand that this should know about recursion. So when you go to a recursion operation, you pass the placeholder, and this is the body computation. So it's going to traverse the computation, and when you return something here, the computation in here is going to be this one. This placeholder is going to carry the return value. So if you go the recursive case, okay, you go for it, go to the left. Okay, so this is a placeholder. So okay, I'm gonna go back into a recursion and keep on going. So that's how they connect the recursion in a functional way, without control flow, without for loops, without a function call. So that's how they are able to model this. So this is how they are able to apply optimizations such as dynamic batching and specialization. So they also mentioned that when you lower into this one, you can apply optimizations like unrolling, tiling, because they are extending the tensor compiler. Yeah, as mentioned before, linearization does not involve tensor computation, and it allows the separation of the recursive control flow from the tensor computation. So this is key, basically, to allow being able to use something like this in order to get the for loops and do all those optimizations. Okay, now the author goes to talk about the recursive API, which is what we saw in here. Okay, so the user can provide arbitrary graphs like this one as input, but they have to specify the number of children per node. For in this case, it's a binary tree, so I guess you have to tell the compiler that you're gonna have maximum of 2 children per node. So that information is going to be used to be able to linearize it and to be able to handle the recursion. Okay. Of course, as in any optimizations, data dependencies, when optimizations are applied, have to be maintained. Otherwise, it's invalid the optimization. And partial ordering allows exploitation of parallelism and other hardware features. Okay, so here he talks about unrolling some of the optimizations. This is one of them, unrolling. So it has a figure for it, and it shows before unrolling and after unrolling. And notice that after unrolling, you can group some nodes and apply optimizations between them. Okay, so the author is going to talk about the optimizations again. Dynamic batching, which basically involves the batching operators on the fly to exploit parallelism. This basically dealing with the data. You have specialization, that sometimes you have some computations that hinder hoisting and constant propagation, and can have execution overheads. So it's like I understand that this is like separating loop nest to get those checks out of the main computation. So you have basically get the problem out of the way in a separate for loop. That's what I understand. And then you have the unrolling, which is something like this, that allows the parent and the children to be reused and creates opportunities for kernel fusion, which is hard for in recursion. So you combine this unrolling, like grouping like this, with some recursive refactoring, that when you put them together, you have the situation that this is before the refactoring. You have A1 followed by A2, so you have this sequence in a node, A1, A2. This is the recursive boundary, and you have the Bn in the lift, only B, this one and this one. Now after the unrolling, you have this grouping here, and you have A2 at the root, and then you have, okay, I execute this one, which if I'm a leaf, I'm gonna go B. I'm gonna go B if I'm a leaf, and then I'm gonna go A2. So I go back to A2 in the recursion. So if I'm not a leaf, I'm gonna go A2, and then go A1. Yeah, like this. Actually, this is A1, my bad. So it's if I'm not a leaf, it's gonna be A2, A1. So A2, A1. So these are different grouping. So now the recursion is back here, so you have some level of fusion, and you can perform optimizations in there. Okay, now in section 4, he talks about lowering the recursive API into the irregular loop IR, which is basically lowering from a high level, I would say functional, into iteration space. I mean, to for loops. So the for loops become explicit. So you can see in the lowering of the for loops that there's another structure that holds the indexes for the nodes. It's called internal batches, and you can see that it has the number of the current batch that you're operating it. So you have a number of batches. So this becomes clear when you see here. You see that you have the leaves batch, which you have 5 in them. You have the internal batch, 2 on them, and this is 1 and 1. And you also have the left and right nodes. So when you iterate through the internal batches, you have like 4 batches, and you go to the first batch and you get the batch size. You see that the batch size is the first one is 2, 1, etc. So in here, first you process the leaf, and you know that there's only one leaf batch. You know the size. So from the leaf batch, you iterate through it, get the node, and from the node you get the word, get the embedding for each of the embedding elements, and then you populate the recursive node. Then you enter in here and go through the internal batches. Go through the each batch is gonna have its size. Get the size of the batch, and from the batch of size batch, basically you iterate. I mean, from 0 to the size of the batch. So you go through each element of the batch, and for that particular batch in particular, get the node, and then you get the value for the left, for the right, and then you get the left hand side and compute the tangent, and you put in there. So this will be the naive implementation. But if you notice that this is dynamic and the indexing here is non-affine, but this is naive implementation. If you use scheduling primitives in there, it's going to look much more ugly, but more efficient. A correction: this is not the naive implementation. By default, the ILIR iterates over all the nodes, but when dynamic batching, one of the optimizations is present, you're gonna have these structures like here. Okay, so now it's gonna talk about data structure linearization, which is basically we're going now in the map. We're going here, section 4.2. Okay. So here's the code to do the linearization, do the dynamic batching, and notice here that in the lowering, in the ILIR, that you use in these structures for batching, the internal batches, then the leaf batch, those structures are populated in here. That's the dynamic batching, and basically it allows you to be able to identify in these batches what can be executed in parallel. So the data dependencies have to be kept in this linearization process. And this high-level representation allows hoisting computation, hoisting propagation, something other approaches can't do. Okay, so the author is going to talk about these irregular loops IR. Yeah, so I have another correction. Before I said that when you lower to ILIR, that's the place where you apply the scaling primitives, but still at this point, the computational optimization are still separate, are specified separately. So still there's potential to apply scaling primitives like loop tiling or rolling vectorization, etc. So still we are at the high level, and it's consistent with what we see in the picture here, that we lowered from a recursive API to the irregular loop IR, and then we even lower even more to the actual for loops that process the linearized batches. So we are not done with lowering yet. So this is a little bit different from other DSLs in which you don't see for loops. Like Halide, TVM, you don't see for loops in there. But we are getting for loops in here, and still with the possibility of applying scaling primitives, if I'm understanding correctly. And so they can have indirect memory accesses, loop bounds, they have non-affine index expressions, and yeah, they have to have conditional operators. Yeah. Okay, so this section is about indirect memory accesses, which are introduced with this IR. So in this lowering to this IR, they have to perform a bounce inference, I guess a dimension inference as well. And yeah, it mentions that like other tensor compilers, this is more difficult for this type of recursion algorithms. Yeah, that is something similar. Halide also have to infer their bounds and things like that when they lower from their functional, the functional shape into the Halide IR. They also talk about the possibility of having data layout transformation, and they provide primitives for that. They can also change that with split, reorder, fused, these traditional scaling primitives. Okay, so let's go to figure 5 is to show what is happening with this data layout. So they have this example in which they have the computation of the indexes, which are using affine, non-affine expressions. And sometimes optimization can come from sometimes optimizations can come from changing the data, like it is being done in linearization. So in here is another case where optimization is done on the how do you rearrange the data. So by doing some data layout changes, then you can avoid having to do this non-affine indexing expression. So then your expressions become affine, and your memory becomes more dense and more compact. So that's the value of doing these data layout transformations. Okay, and of course they have to lower the conditionals to if statements. Okay, now let's go to the implementation section, which is very short. This section talks about some details of the implementation. So the optimizations that they support is dynamic benching and specialization, as mentioned. I found this interesting. They are extending TVM. Of course, this is coming from OctoML, but also they're extending tensor compiler, and it seems like this comes from Halide. I don't know exactly how they do it or what does they mean exactly by that. And they do not have auto-scaling, but I understand that they had the potential to have it, so I guess that's future work. And they do the manual optimization. They use some grid search for auto tuning, and also they have some numbering scheme for the linearizer, which is described in the appendix. So now let's go to the evaluation, which is how they collected their numbers to compare against CAPS, DINET, and PyTorch. So as mentioned before, CAPS and DINET are the 2017 state of the art, and that have demonstrated to be faster than generic frameworks like PyTorch or TensorFlow, and they evaluate these systems in Intel ARM CPU and also in NVIDIA GPU. Okay, so the models used for the experiments are listed in table 2. As mentioned at the beginning of the video, they are testing against recurrent neural networks, GRU, LSTMs, and RNNs, and this comes from Stanford's sentiment tree bank, the last three. They use the hidden size of 256 and 512, so they are going. This HS means small, which is 256, and HL large 512, and they're going to use a batch size of 1 and 10. Okay, so figure 6 compares a CORTEX against PyTorch, and as mentioned before, it's not even the state. PyTorch is not the state of the art, so they try all the benchmarks, and the speedups are ridiculous. 200x, I understand, because basically it's showing that PyTorch is doing very bad. So this is the batch size. It basically gets worse as the batch size increase, and the reason for that, the author says that it is that they do not have dynamic batching or kernel fusion, which limits their ability to exploit parallelism. And also they limit the PyTorch ability to do data reuse across batch elements as well. Yeah, so these are the platforms that they are using: NVIDIA, Intel, and ARM, and the corresponding software, CUDA, MKL, and Agent. Okay, now instead of comparing against the poor PyTorch, it's going to compare against CAPS and DINET. So they have a speed of up to 14x, which is pretty good, but not as huge as against PyTorch. And compared to CORTEX, CAPS, and DINET includes significant overheads unrelated to tensor computations. And if you go down a little bit, these are the overheads, and you have a list of kernel cores, CUDA, execution time, memory management. And I understand that many of these do not have anything to do with tensor computations. Okay, so there are various sources for that overhead. So DINET and CAPS implement a generalized runtimes algorithms which cause overheads in dynamic batching and graph construction. DINET in particular constructs a data flow graph and performs dynamic batching on it. So it handles a larger graph than CAPS, and yeah, that's a typo from my side. CORTEX does the dynamic batching. It is limited to linearization before tensor computations are executed, and that's an advantage. CAPS and DINET are use vendor libraries, which has the contiguity checks, and those checks produce overheads. CORTEX does the whole compilation process and does not need those checks. So that's another disadvantage of using generic libraries. So you have extra checks. Okay, so this is a DINET comparison. Let's go first to the comparison against CAPS. So these are the speedups. These are the 3FC, the GRU, and the LSTM. And this is small size 256 and large size 512 with the batch. I don't see any relationship between getting larger batch and getting larger in hidden layers and a speed up. Actually, you get the higher speed up with the small size and batch size of 10. So yeah, and When you get bigger, you get less speed up, but still it's significant. Yeah, for background, CAPS is a vertex-centric programming. That's the name of the paper, published in 2017 by Carnegie Mellon and the Tsinghua University, and it's an interface for dynamic neural networks. Okay, so in here, it is comparing against DINET. So at lower hidden sizes, so you vary the hidden size from low to large, and this is GPU and CPU. For low hidden sizes, the inference latencies are quite high and are mainly comprised of overheads. So yeah, so CAPS and DINET. So that this is both of them. It's basically showing the overheads that you get, and so so for the case of CPU, the overheads increase exponentially for some reason. So yeah, that's a problem of the overhead. So now the actual comparison with DINET. So in the case of DINET, it seems that CAPS is a little bit more limited. The data is less, but for DINET, more experiments could be where he was able to make more experiments. So DINET, the name of the paper is Dynamic Neural Network Toolbox, developed also in 2017 in collaboration with DeepMind, IBM Watson, Carnegie Mellon, University of Edinburgh, which does a lot of deep learning for compiler stuff, and also Google and Microsoft Research, and many others are involved in that paper. So it looks like DINET could be a little bit better according to this data. You can cover more cases also. So let's see how actually better it is, and actually I think it's better because the maximum speed of 14x was against CAPS, but it didn't got that 14x speed up against DINET. So actually DINET performed better in some cases, like this one. So again, you go from small to large, from small batch to large size, and I don't see relationships between the getting better speed up at higher sizes. It's kind of random. It looks a little bit random, but you can see in average that Cortex does much better. You get up to almost 10x speed up. Actually, this is not my bad. It goes close to 14x for GPU. For the GPU actually looks better, but also I got a 9x for ARM. And for Intel, it did well. It did well for Intel, so it did well for all the targets. Some better than others. Okay, so which the LSTM did well. Actually, the major speedup came from LSTM, and also from GRE. Yeah. Okay. He mentioned the benefits of optimizations. Complex models such as 3LSTM provide more fusion opportunities. Specialization enables computation hoisting and constant propagation. It seems that they kick in for LSTM. Maybe that's why it has a 13x speedup. Okay, so it talks about other scaling primitives, some rolling. So he mentioned that before. A recursive refactoring, which reduces the number of global barriers in the GRNs. And yeah, for 3GRE this does not give significant speedups. Okay, so here it shows the difference between DINET, CAPS, and Cortex. So you have DINET that it shows the recursion boundary and the kernel boundary. So CAPS is able to get more kernels. This is able to do fusion in here. So you can see that there's register reuse in here. So DINET has nothing for global optimizations. So now Cortex is able to fuse everything into a single group. And you can see the register reuse, you have the shared memory reuse. Also you see here that you have the W and the bias. W and the bias for the LSTM. I think this is an LSTM, right? Doesn't say which type of algorithm, but anyway, it's similar to one of those layers. So you can see the W on the bias in here that is computed every time, but here it realizes that it can be reused, so it's cached. And the bias is also cached. That's something that the others do not do. That's what they meant about hoisting those. And you have global memory reuse as well in here and in here. So there's a bunch of optimizations that, well, actually these have global optimizations, global memory reuse, but they don't have much of shared memory reuse and register and yeah, that hoisting. Okay, so yeah, so you can see here the comparison in inference. Again, Cortex was made for inference, not for training. So comparing these benchmarks, sequential STM, sequential GRU, with the two batch sizes. Okay, so these are the hand optimized. So he's comparing a hand optimized versus Cortex. So in this one is sequential LSTM, and the Cortex is able to perform closely to this one, to the log base, but the one that doesn't have a log performs much better. So yeah, it's hard to beat the manually optimized implementation, but again, it's not practical also to do manual optimizations for everything, I guess. So I guess as long as the portable version is close to the manually optimized version, they are good. That's probably what they trying to show in there. Okay, he made some comments about the memory usage. He said that PyTorch uses the least amount of memory because it does not perform dynamic batching. DINET and CAFs were designed for deep learning training and inference, unlike Cortex, which is designed only for inference. And DINET and CAFs, intermediate operations computed during the forward pass do not free memory used by these intermediate tensors, so are not very memory efficient. Cortex, on the other hand, materializes fewer intermediate tensor because of the nature of kernel fusion, global memory reuse to kernel fusion, and also DINET requires extra cache space to ensure contiguous inputs for vendor libraries. So yeah, here are some more graphs, results. So let's go first to the memory. This is what the section that I was talking about, that PyTorch is the most efficient in memory. It has nothing for this example, but for this one is the lowest and lowest because it does not perform dynamic batching, but not everything is memory. Also in performance, PyTorch does pretty bad, as you saw before. This dynamic batching is critical for performance of inference, reducing the runtime of inference. So DINET and CAFs do, from the comments, they did pretty poor. They do not deallocate all the memory that they have. So Cortex, which is the orange one, actually CAFs is terrible as you can see. And DINET sometimes is pretty bad. So Cortex, yeah, is pretty much low memory. Okay, so these graphs in here try to show the advantage of some optimization. So they're not comparing Cortex against DINET or CAFs or PyTorch. They are just comparing the optimizations on themselves. So this is the latency in milliseconds. So the first one is no kernel fusion, nothing. So okay, if I do kernel fusion, I get some jump. So this is for batch size 1 and 10 for all the 4 benchmarks, and you can see that doing fusion, it didn't help in here for some reason, but it did help in here. Fusion helps in here, helps. Usually doing fusion is good, and this is a huge help in here. Okay, once you do fusion, you apply specialization and then apply persistence. So then you apply specialization and persistence, and you see that the combination of them gets a way lower latency time for inference. So sometimes things get a little worse, but usually it's going down. But not optimizations are good all the time. For example, now you have unrolling, and you have the RNN, and you have the LSTM. And then he puts the example of LSTM that when you do unrolling, you get additional barriers. So in here, the inference gets worse when you do unrolling for both batch sizes. But for RNNs, that's not the case. The unrolling is helping. So recursive factoring is somewhat similar. For 3GRU is good. For simple 3GRU is good, but not for this one, for this case. So yeah, I guess that's the job of the autoscaler, to figure out which scaling primitives to use for the particular problem. Okay, so let's go to the related work. One of the things interesting I found is that CORTEX, he mentions that CORTEX could be potentially be built in MLIR. And a related work related to optimizing dynamic networks, of course, DINET, CAFs, BatchMaker. Unlike these, Cortex performs dynamic batching before tensor computation. That's a key of insight of this paper, that the linearization and the batching is performed before the actual computations, and then the fusion between nodes allows things, optimizations like persistent RNNs. But yeah, basically points out where persistent RNNs were first published. Cortex is able to extend recursive models and formalize them as transformation primitives. That basically, yeah. So basically, he points out that these optimizations were manually presented, and now there's scaling primitives for them in this DSL. And of course, Cortex currently focuses on cyclic data structures, like the binary tree we saw in the input example of this paper. And yeah, Cortex borrowed from the work techniques. Yeah, so there's some inspiration for indirect memory accesses taken from sparse polyhedral framework. And yeah, so as a conclusion, Cortex is a compiler for optimizing recursive deep learning models for fast inference. So yeah, basically this paper looks good. Looks like an elegant DSL that is able to beat the state of the art and open up the possibility of applying an autoscaler to this type of recurrent layers. And I tried to find the GitHub for this, but I was not able to find it. So if you know where to find it, please write it in the comments. So that's it for the video. Thank you very much for watching.